everybody. Welcome to our GPCE seminar. Today we have Stephen Eubank, who's from UVA. He's the Deputy Director of the Network System Science and Advanced Computing Division, and also a professor in the Department of Public Health Sciences. So I just want to welcome him and turn it over to you, Stephen.
Hi, and thanks. So in this seminar series, we've heard a lot of really great talks on optimizations and modeling and public health applications. And I just want to warn everybody that this is not one of those. This is going to be fairly theoretical, and its connections to actual public health are a little bit tenuous, but I'll try to show you where they come in. This is work that I've been doing for the last few years with a bunch of students, as well as some people in the group. It's entirely my fault. It's not their fault. I just want to start off with that as well. I'm going to talk about the context of contact networks for the spread of infectious disease. And a lot of our effort goes into figuring out how best to target interventions, whether they're pharmaceutical or non-pharmaceutical, so that we slow down the spread of disease or reduce the morbidity and mortality due to disease as much as possible. So this is an optimization problem. We have pharmaceutical interventions that target usually a subset of vertices, the people in the contact network. And non-pharmaceutical interventions can target either people or the actual edges, the contacts themselves. And the efficiencies that it's possible to gain with a good optimization, or something in this cost-benefit sense, with cost and benefit functions defined on subsets of people or contacts. They might be economic, they might be disease-related. Anything is fair game. Because these are basically percolation problems with a phase transition in the system, there's a highly nonlinear response near that phase transition. And that means that you can get extremely high efficiencies if you do the right things, i.e., you can have effects with pharmaceuticals that are much larger than just one case averted by one dose. How high can the efficiency get? It's really hard to know because we don't know what the optimal targeting is. So this talk is really going to be about optimal targeting. Yeah. Optimal targeting is a really hard problem. Not least of the reasons for this is that if you've got a system with n things in it, either contacts or people, whichever you're targeting, there are 2 to the n possible subsets of targets. And really, you need to basically sample possible targets, and you need to evaluate the possibilities for each sample you take, so that the probabilities of outcomes on each sample of targets. And there's no way to avoid simulation. This is not an analytical problem. On the other hand, 2 features of the problem that are very important are that a small local change in the network can have global consequences that are very large across the whole network. Although it has to be admitted that sometimes a small local change has an extremely small consequence. So when you're doing an optimization of an intervention, you have to deal with what's usually a very, very flat landscape that has deep holes in it at places that you don't know ahead of time. And to my mind, this means that simulation itself, although it's required, it's not enough. You have to combine it with analysis, or you just won't get the right optimum. So optimal targeting, it's hard. It's not a problem that we're going to solve anytime soon. And it turns out that even approximately optimal targeting is a hard problem. What I'm going to talk about today are ways to get pretty good bounded approximations for optimal targeting with controllable errors and a controllable trade-off between how good the optimum is and how much time and effort you spend finding it. So what we want to do is change the structure of the network to achieve some goal. And there are a lot of ways to measure network structure. I just listed a bunch here in no particular order. Some of these things are expensive to compute, as expensive as, well, not as expensive as doing the optimization, but expensive nonetheless. Most of them are not really feasible for public health. So even degree, which we heard a talk about from our lab just a week or 2 ago, if you talk to people at CDC, they're generally pretty skeptical about targeting interventions by contact degree. So imagine going to them and saying, well, I'm going to use shortest path between us to target the nodes that I'm going to intervene against. It's not going to work. But I think there's a problem that's even worse about these, is that once you've measured your statistics, you still don't know exactly how it relates to the problem you're trying to solve, which is reducing the size of an outbreak, say. You have to do some sort of analysis, make assumptions, write papers to figure out how modularity is going to be connected to the dynamical system. Because of these things, we really don't know how far from optimal the solutions we're proposing are, except in the case of really small or really highly structured networks, or maybe very random networks. And the reason is that this is a chicken or an egg problem. And we've known this for at least 60 years. And the way that Rappaport and Horvath characterized it in this article is that you'd think we could build a taxonomy of networks based on statistical parameters like the ones on the last slide, and then say, okay, let's find out which regions of this space, this taxonomy, have particular characteristics with regard to the spread of infectious disease. But which parameters you want to use depends on the taxonomic considerations, like how disease spreads on networks with those values of the parameters. And you can't solve one problem without the other. You can't do them in isolation. So there's a way around it that's even older than this 60-year-old citation, which is Moore-Shannon network reliability. And this isn't the way they posed it, but this is basically what they're talking about. Given some dynamical system with some set of configurations, and there's a cartoon of one down here, this particular dynamical system always goes to a fixed point. So I'm going to be talking about systems like that for a while. I want to know what's the probability of reaching these particular configurations, any one of these in green, given that I'm starting off in this gray one over here. If you can answer that, you don't really need any more arguments relating that statistic to the dynamics, because what I've said is I don't want to see any dynamics that get me to the solution that the state of this last element is 2. That's what the green nodes there are. And I can make any collection of these states that I want. This question of what's the reachability of some configuration given your starting configuration in the dynamical system, it shows up all over the place, particularly that I know of in statistical physics and field theory. But it's a Bayesian network problem. It's just all over the place. The way I'm going to pitch it today is in terms of satisfiability. Oh, and just for future reference, I could have taken this network and identified all the green configurations as one and all the red configurations as the other. And for future reference, notice that in this particular system, if it doesn't go to the green state, it has to go to this state. So this is just something to remember when I start talking about invariance in the problem. So what is this equivalence between reliability and satisfiability? If I have n independent events that occur with probability x twiddles of I, I'm going to think about these random variables, e sub I, that indicate whether or not the ith event occurred. And then I can write down a logical expression, which is essentially the same thing as picking some of those configurations and saying that they're the ones I want to reach. And here I've displayed the logical expression in disjunctive normal form. Then the question is, the stochastic satisfiability question is, what's the probability that this expression is true? The deterministic satisfiability problem is something like counting the number of assignments that will make that expression true. In this case, you're counting the number of assignments, but they're all weighted by some probability of being true. So you get an expected value that this thing is true. So here's an example of how you get from network reliability to satisfiability and back. I'm going to consider this little toy network down here, and I want to start an infectious disease at person S, node S, and I want to know what the probability is that it reaches node T. And I'm going to assume for a while in this talk that these are homogeneous systems. So the probability of a transmission between any two people is going to be X, the same for every pair of people. The answer to this question is, well, there's only three ways it can get from S to T. It can go the high road, or the middle road, or the low road. And like in Loch Lomond, if you take the low road, you're going to get there faster because there are only two hops you have to take. Each hop has the same probability, so it's more likely that you'll go this way. But you can imagine that if this were longer or shorter, if there were more of these parallel paths here, it might be the case that going through the top road actually gives you a higher probability of reaching T than going the bottom road. Here's an expression. Here's one of these disjunctive normal form expressions that is exactly the same as saying you either go to the top root or the middle root or the low root. You either go through events 1, 2, and 3, or you go through events 1, 4, and 5, or you go through events 6 and 7. One of those three things has to be true in order to get from S to T. And by the way, there's another picture of this, which is this one. This is just the Markov graph of this particular system. The reason that's kind of interesting is that it means that this transmission, SIR style transmission on a network, is a sort of universal way of thinking of the problem. Because I can map from any of these expressions, if they satisfy certain constraints that I'll mention later, I can map from these expressions back to the graph. And the problem turns into an ST reliability problem. So what's the probability of from some starting point, I can reach some finishing point under SIR dynamics on this network, which is determined by this. So there's a nice reduction there and equivalence that lets you cast an enormous number of these reliability problems in the form of ST reliability on a network. I'm not saying that it's easy to do it or not computationally complex, but it's possible. So here's the problem we want to solve. What do we have in our toolbox to solve it? Not very much, but we'll see how powerful these things can be. So we've got unitarity, which is a fancy way of saying that the probabilities are correctly normalized, so that the sum of the probabilities over all the possible ways that things can turn out, it's got to be 1. The probabilities are positive or they're non-negative. And I'm going to add one more constraint, which is monotonicity. And in the satisfiability world, that means that the expression contains events with only one sense. So if this positive sense that the event happened appears in the expression, then the negative sense that it didn't happen does not appear, and vice versa. Unitarity, not too surprisingly, it imposes a symmetry constraint, which has this unfortunate consequence of, you would call it a duality relationship in most things. So unitarity gives you duality, oddly enough. So what do I mean there? So the probability of an event not happening and an event happening has to sum up to 1, so you get this relationship between them. And this holds for compound events as well as individual, the basic events. So the probability that the expression is true is 1 minus the probability that it's false. Here's the DNF for the expression itself. Here's the DNF for the negated expression. As I said, you can construct a network that this is an ST reliability problem for. Similarly, in the dual world, you can construct a network that it's a problem for. So these networks are, in a sense, duals of each other. The probability of getting from S to T in this network is equal to 1 minus the probability of getting from S to T in that network. And as I said before, I'm not saying it's easy. Even if you're given the DNF with all the possible clauses in the expression, translating it into the DNF form of the negated expression is expensive. Okay, so that was one of the properties.
Even can you go back?
Yeah, sure.
So that one seems a little bit, so 5 and 4 are parallel edges. Did you mean sequential edges there in some form, or really parallel edges? Because
no, these are parallel. So if, for example, if I cut the probability of getting from S to T in this graph is 1 minus the probability of not getting from S to T in that graph. I may have said that wrong before. So
right.
a cut in this graph corresponds to a path in that graph.
Okay,
If
so
I cut
not
1, 4, and 5, it corresponds
so
to
not
this
getting is
path.
correct,
Yeah.
because one of 5 or 4 gets cut, then you won't. But
Right.
here in the parallel thing, 1 of 5 and 4 gets cut, you won't make it on that path, right? In a parallel one, both have to be cut, or one of them gets cut. My
Right.
point is, in the old graph, if 5 or 4 gets cut, then that path is cut. In this one, it's the reverse. But okay, I'll take a look at it.
If 5, yeah.
Yeah.
It works, but sometimes I get my negations in the wrong place and my 1 minus is in the wrong place.
That's okay. There's other small point, and I should continue, and we can talk offline, is the term stochastic sat is used for a particular form of satisfiability in at least in the sat world, where you're talking about quantified versions, where you think of it as players, 2-player game, where you control that there exists quantifier, and then a random player controls the random quantifier. So so you might want to change the definition slightly different. Your problems appears slightly different than the traditional definition of stochastic sat.
Okay, thank you. Yeah. This monotonicity constraint is actually fairly strong. It restricts not only the possible expressions you can have, but I suspect that it restricts the kinds of dynamics you can look at. I need to investigate that more thoroughly. However, since we're in this epidemiology world, it's good to know that the size of an outbreak under like SIR kind of transmission dynamics, where there are independent transmissions on different incoming edges, that is a monotonic problem, monotonic kind of dynamics and a monotonic expression. If you add another transmission to the transmission that you've already got, it's not going to make it not satisfy the expression. So monotonic problems have monotonic solutions in the sense that I had this variable X, which was the transmission probability in my example network. The probability of the entire expression is a monotonic function of X. Monotonic SAT problems admit the notion of minimal clauses. All right, so what do I mean by minimal clauses? Here's a simple expression, and it has 4 variables. They're binary variables, so there's 16 possible states for this system, and each of those 16 is represented here. Each one of those states is labeled redundantly by, on the top row, which events are true, which events occurred, and on the bottom row, which events did not occur or are false. It's redundant, but it's kind of handy for some ways of looking at this. So now there's shapes and circles and colors and stuff. The circles are all configurations where the expression is false. And I'm going to call those cuts. And I know that it has a very definite meaning in computer science, but this is a very closely related concept. The squares are the remaining configurations. Those are the ones that make the expression true. The ones that are filled are not minimal. The ones that are not filled are minimal. What do I mean by minimal? Well, if I add any of these cut variables to the top row, if I move it from the bottom row to the top row, I'll end up with something that's not a cut, which I call a strut. So going from this circle by moving any of these edges up to the top row gives me a square. This is different from a minimum, right? This is a minimum cut. This is a larger cut, but it is still minimal in that sense. So this might help see what's going on if I add the edges. These are all the transformations you can make, the movements you can make in this lattice by moving one of the numbers from the bottom row to the top row. And the lattice is laid out so that on each row, the same number of variables are true or false. The thing about monotonic systems is that you can draw this separatrix as a continuous curve that cuts across the entire lattice, such that everything above it is a circle and everything below it is a square. And that means that there's actually a very general purpose way you can sample the minimal cruxes. First, you find out where the separatrix is. You can take any random path from here to there through the lattice and do a binary search along that path until you find out where the separatrix is. Then you can walk along the separatrix until you find something that's actually minimal. Now, this is never, ever going to be as good as a bespoke algorithm. For example, if your expression is something about existence of a path from S to T, they're pathfinding algorithms that'll do much better than this performance, but it's general purpose. So I know that I can sample from these minimal cruxes with some effort for any expression that I've got. Why is that important? Well, it works well in combination with these limits as x goes to 0 or 1. So here's how the limits x go to 0 work. I'm letting the probability of transmission, for example, go down to 0. And I'm thinking about this inclusion-exclusion expansion, which is to recursively apply this simple expression of unitarity again until none of these expressions, A or B, contain any disjunction. So I'm going to turn this big disjunction into a bunch of conjunctions. What happens when I do that? Well, the conjunction of any set of k independent events is going to be true with probability x to the k. X is the probability of any one of the events, so there are k of them. That's the probability of all of them, and they're independent. Whereas the inclusion-exclusion expansion plugs in some power of x for each one of these things because they're all just conjunctions. So you get a power series in x, which is the same thing as saying a Taylor expansion at x equals 0, because the powers are all positive integers. So this expansion is the weak coupling expansion of statistical physics. Notice I didn't say it's analogous to, it's not like it, it is the weak coupling expansion of statistical physics, which is one of the workhorses for finding out what the consequences of your Hamiltonian are. However, when you truncate this expansion, which has like 2 to the n terms, where n is the number of events in here, the truncated expansion typically violates both unitarity and monotonicity, which are basically the only things we have in our toolbox to work with. So if you're watching carefully, you notice that I just switched slides. You can do this exact same thing as x goes to 1. Everything's the same, except now you have an expansion in terms of 1 minus x, which is a Taylor expansion at x equal 1. So what do I mean here when I'm saying that the truncated expansion violates unitarity and monotonicity? Here's an example. I've got some particular problem I'm looking at, and I use just one crux. So I'm truncating that expansion with the probability of one crux occurring or not occurring. And this is the expression for the probability of the whole expression that I get. They violate unitarity because they go outside this box, and these happen to be monotonic. But now I use 2 cruxes, and they're no longer even monotonic, and they're still violating unitarity. And I go to 3 cruxes, and it's this problem. So this is the problem of connecting up the strong coupling and the weak coupling approximations in physics. I don't know what it translates to in computer science and satisfiability, because it's a slightly different way of thinking about how you do the approximations. You've got these 2 Taylor expansions from here and from there, it seems like it ought to be really nice just to sketch what the interpolation is. It's got all kinds of smoothness properties. You know, it's a finite degree polynomial. And the answer that I'm going to try to convince you of now is that, yes, you can do it. And in fact, you can do it using basically computer-aided design curves. So you can go into Illustrator or your favorite package and draw some derivative tangent surfaces here. And the solution is really the best solution that you could want. So for example, in this case, I'll build a Bezier curve interpolation of these two things that turns out to be extremely close to the right answer. And it also allows me to construct these bounds on where the right answer could lie, given the information I have from the derivatives at x equal 1 and x equals 0. How does that work? Well, we all know that degree n polynomials form a vector space. We probably don't think of it that way much, but they do. And the Taylor expansions, the power series, are really one basis, the power basis for these polynomials. Here are the basis functions. I never really think of them that way, but this is what it is. It's just a decomposition of this vector into its coefficients in these bases. And the problem with power series is that fairly simple behavior near x equal 1, like this kind of behavior, has to be modeled with really large alternating sign derivatives, high order derivatives, if you're going to model it with a Taylor series around x equals 0. And this stuff in red should frighten anybody who's trying to do numerical analysis on very large systems where they clearly will not be able to do it in a stable way. Now, there are other bases that are possible for this vector space. So this is the Legendre basis. It's nice because the basis functions exhibit this symmetry that makes it very interesting to use. However, the one I really like, the Bernstein basis, is a remarkably useful alternative. So these are the basis functions in the Bernstein basis. This is the expression of some function of x in the Bernstein basis. That's the Taylor coefficients and the Bernstein coefficients. And these are plots of this function for n equal 6 or 7 or something. They exhibit the same reflection symmetry that the Legendre polynomials do, but they also have several other properties. So they have this convex hull property, which I'll explain more in a minute. But basically it says that if you know what these coefficients are, you know where the curve has to lie. You've got a box, a bounding box for the whole curve. They're also localized in ways that the Legendre polynomials aren't. And they're normalized. I guess everything's normalized, but this is a particularly simple normalization that at any given x, if you sum over all the basis functions, you just get value 1. And there also happens to be a very nice, stable, numerically stable algorithm for evaluating these things. It doesn't require you to take a lot of combinatoric binomial coefficients. And lastly, the transformation from Taylor's, the power basis, to the Bernstein basis is just a change of basis transformation. And in this case, it happens to be lower triangular. So what are some of the consequences of all these nice properties? If you put together the reflection symmetry of the basis functions with the duality that we mentioned before, and the fact that a partition of unity gives you a really simple expression for 1, it implies that the Bernstein coefficients in the original problem are just 1 minus the reflected Bernstein coefficients in the dual problem. So if you know the first k of these, say, and the first k of these, you'll be able to constrain this function at both ends. The convex hull property allows you to get unitarity in the function that you construct simply by making sure that all your coefficients are in the interval 0 to 1. Similarly, the locality property lets you enforce monotonicity by ensuring that all your coefficients are monotonic. And finally, the triangularity of that transformation says that if I've got exact values for the first few Taylor coefficients, then I'll get exact values for the first few Bernstein coefficients at each end. So even if I truncate the Taylor series, which, if you remember, the Taylor series came from that inclusion-exclusion expansion. If I truncate the inclusion-exclusion expansion, I can still get exact values for these coefficients. If I do all these things together, I can construct tight bounds. So this is the picture I showed you before. Now I'm revealing what the mystery function was that I took the Taylor coefficients of. So you can see this is the first couple Taylor coefficients of that function. It's not so obvious, but these are the first couple Taylor coefficients of f of 1 minus y. So here are the control points that form the convex hull of the function. And you can read these points off of these Taylor series. I'll just say that. Furthermore, there's only one coefficient missing, because I know that the ones on the left and the ones on the right are related in this nice reflection symmetric way. And I know that this is a degree 7 polynomial. There's only one coefficient that's unknown. And monotonicity tells me that it has to lie somewhere in this interval. So if I assume it's the bottom one, I get this bottom edge of the region that I showed before. If I assume it's the top one, I get the top edge of this region I showed before. Because although the basis functions are local, they do have non-zero support over this whole interval. So there's some influence of these things on this shape of the curve even here. Moreover, if I just do a linear interpolation between the ones that I know, the left and right edge of the ones I know, I get this. And that happens to function because there's no order 4 term here. So how good this interpolation is depends on how much structure there is in this function in this area. I know what the structure out here is, and I know what the structure over here is. I'm not certain what the structure in here is. And that's where this range of uncertainty comes from. Okay, so now let's go back to a little bit more applied stuff. Using all those tools I've described, we have ways the reliability of fairly large networks. So I'm going to look at School 86 in the AdHealth data. The reason I'm looking at School 86 is because there's an R package on exponential family random graph models, builds random graph models from the data for School 86. And those networks within the ERGM assumptions, the same degree distribution, the same clustering distributions, and you can constrain other statistics too under this ERGM mechanism. I'm going to take all those random graphs and compute the probability of observing an SIR outbreak that affects more than 5% of the students in that network using the reliability tools I've shown you. Okay, so the different colors here are distributions that I get from networks constructed by constraining different features of the random graph models. I think this one is just constraining the degree distribution. This is constraining some combination of degree and clustering, etc. And what I want to point out here, the probability of observing such a big SIR outbreak goes up, as you would expect it to monotonically. But the actual School 86 is this purple curve here. It's complete outlier. So none of these ERGM networks are actually a good model of the way this outbreak will behave with this statistic on the original data network. So evidently, constraining degree and clustering, things like that, is missing important structure in this particular social network. It leads you to make the wrong hypotheses about how an infectious disease will spread on the network. Stopping here to summarize a little bit. So reliability itself provides a very direct characterization of network structure. I don't have to argue from this plot to something that's really meaningful. This is the attack rate, the probability of the attack rate's greater than 5%. So it's possible to do useful approximation. Time complexity I didn't talk much about, but I said you had to truncate the degree distribution. You have to sample the the struts, the cruxes. You can't do it exhaustively because there are a combinatorial number of cruxes possible. So this is not a trivial computation. It's a pretty nasty one, but it gives you a really nice result. And I don't see how we're going to make particularly tight bounds on the error complexity trade-off because it's inherently problem dependent. It depends on exactly what the distribution of cruxes is. However, the approximation does obey the known constraints. It works for fairly general systems. They can be directed, they can be multigraphs, and eventually they'll be able to be weighted. And the approximation is embarrassingly parallel. So you're just doing Monte Carlo stuff at some point. However, it's not what I said I was going to talk about. I said I was going to talk about optimal targeting. But now at least I have the function that I'm trying to optimize. And that is something called Birnbaum importance, which is basically just you leave n out, you recompute the reliability, and you see how much you've made it go down or up, depending on what you're trying to do. Again, evaluating the reliability is hard. Approximating it is hard. It's complex. You don't want to have to do this for an exponential number of possible ways to leave n out. So it would be nice to have a greedy algorithm that chooses the best thing to leave out at each step. Unfortunately, reliability is not a submodular function in terms of the vertices or edges. So you can't take advantage of all the wonderful properties of submodular functions and greedy algorithms. However, it is submodular in terms of these cruxes, these minimal sets that guarantee that the expression is true or false. And this is a complicated thing that I don't understand all that well, but I can show you proofs of both of these facts. So it's possible to develop a greedy algorithm to estimate Birnbaum importance. Of course, because of this global sensitivity to local changes, you have to re-rank the whole set of events at every step. Because when you remove one event, you can completely change the ranking for everything that's left. Also, as I mentioned before, the smallest non-zero importance of an edge, the smallest thing that can happen besides nothing when you remove a single edge is really, really small. And the way that we're doing the ranking allows both some efficiency in computing the Birnbaum importance, but importantly, it allows you a greatly enhanced precision. So I can identify extremely small differences due to removing a single element. So here's an example. These differences aren't extremely small, but they can be small. I'm going to take a generalization of that network that I had before, which looks like this. There's an arbitrary number of these parallel paths. They can be arbitrarily long, and this shortcut can be arbitrarily long. The family of duals look like this. And I'm going to compute which of these two edges has the higher Birnbaum importance. I'm not showing you the importance itself. I'll tell you what I'm about to show you, though. Clearly, if I have enough paths here, and they're not too much longer than the path down here, then for some values of x, you get more of an effect by removing this edge, just cutting out this entire subgraph. On the other hand, if you're pretty likely to get there anyway, you would want to take the shortcut. It doesn't have as much redundance, but it's more likely on each stage. So these two edges cross over in importance at some point. And the point where they cross over is what's being plotted here. So it's a rigorous test of how good the estimation is. I'm not just estimating the Birnbaum importance, I'm estimating the relative Birnbaum importance of these two edges. And as a function of the number of samples I've used, number of crux samples I've used, and the depth of the inclusion-exclusion expansion that I'm using. And I'm looking at a whole family of graphs. Some of them have thousands of edges. And the line here is the true value of the crossover and the experimental result. So what you can see is that as the number of samples goes up, I get closer to the line. As the depth of the expansion that I'm using goes up, I get closer to the line. And it can give me make some pretty good distinctions. Okay, here's a much harder problem. I'm going to take some graphs with tens of thousands of edges in them, and I want to shatter them so that I remove a bunch of edges or vertices, and I want to see if the remaining connected components are all have less than 200 vertices in them. And what I'm comparing, I'm looking at 3 different networks. One's a scale-free network, one is a block stochastic or a planted L partition network. And in this one, I've arranged it so that it's very hard to tell where the partitions actually are in the original network. And this one is a combination of the two, which has the same number of partitions of the same size, but within the partitions and across the graph as a whole, the degree distribution is the same as this scale-free thing. I'm comparing against random cuts, random withdrawals of edges and nodes, degree-based one, like the talk we had a couple of weeks ago, something using Birnbaum importance, which is the yellow curve, and something using an algorithm, a heuristic called collective influence, that claimed at the time to be optimal, but it wasn't exactly sure what they were optimizing, in my mind at least. What I'm plotting is as a function of how many either vertices or on the right side edges are removed, what fraction of the vertices are still in the giant component when I've removed it. And what we see is that although the Birnbaum importance criterion, it's not always doing better. It always reaches its criterion, which is that the giant component has less than 200 edges in it, before the other methods. And sometimes that difference can be startlingly large. So this is, I think, some evidence that this is an interesting way to find the optimal. So what I was complaining about at the beginning was that we don't know where the optimum is. We can't know how well we're doing. You know, we're looking at differences between these methods here. And the optimum is out in left field, and we don't even know that that's where it is because we don't have a good way of determining the optimum. If you can shatter the graph, you can also detect communities in it. So I use the same approach to detect communities and things. This is the set of communities that you would get under collective influence. The reason it looks like this is because the heuristic is basically pulling out individual vertices or pairs of vertices, something like that, to shatter the graph. Whereas the Birnbaum importance is not looking at individual vertices. It's trying to find sets of vertices that you can pull out to make sure that they don't form a connected component with more than 200 vertices in them. And if you allow yourself to get rid of individual edges instead of vertices, you can get an even more balanced network out. Okay, in the last couple minutes, I'd like to talk about heterogeneous systems. So everything I talked about so far is homogeneous systems. The probability of transmission is the same for every edge. And that's clearly not really the problem we want to solve. Unfortunately, I was really hoping to be able to give you the solution here. I don't have it yet. The problem is that the probabilities have to be parameterized by 2 parameters now, not just the average value of the transmissibility, but the dispersion across different edges. You can do this, and you can ensure that when the dispersion goes to 0, you get back down to the homogeneous case where you know how to deal with it. Here's one way to do it, is a power law. It's a fairly natural way to do it. So the probability of transmission on each edge is a function of these 2 parameters, tau and u. And the function is 1 minus u to the w, some weight associated with the edge, times tau. Or maybe you'd want to use this function. They're both very reasonable. These things are suggested by thinking of the interactions as Poisson processes that eventually happen or don't happen. Or you can look at it as a way to get Maxwell-Boltzmann statistics out of the dynamics. Another way to think of it is that you can take a single edge that has a weight associated with it and replace it with that many copies of an edge that has a unit weight, either in series or in parallel. And that's what gives you these 2 different power laws. Unfortunately, the relationship between the original and dual problems is more complicated than it was in the homogeneous system. In particular, because the dual problem, if this is natural for the dual problem, it's really hard to work with for the original problem. And if this is natural for the original problem, it's really hard to get to that in the dual problem. Finally, it also requires some rational relationships among the probabilities just to get these things to come out as power laws with integer weights so that you can make a Taylor series out of them. So another possible parameterization that's not as, it's obvious in hindsight, but not as obvious when you start working on it, is just a linear parameterization. So you can think of this as there's some like mean transmissibility, and then there's a range around that that the weights are all sitting in. It's a somewhat simpler analysis, but I just haven't finished with it yet. The problem in both this and the power law is that although they reduce to the homogeneous case when U goes to 0, the dual and the original problem reduce in different ways. And it's not discontinuous, but it's not C infinity smooth at U equals 0, which gives you problems when you're trying to use the tricks that I had before. But the idea is that you can create a polynomial that's now like a double Bernstein basis, one for the parameter U and one for the parameter tau. And you can find good estimates for these coefficients using the reflection symmetry and the duality property. That's about it. There are a lot of things to do with this. I've really only scratched the surface of this work. I'm particularly interested in comparison to spectral methods. You can just read these. I mean, there's lots of stuff there, but I think overarching all of this is developing what Rappaport and Horvath called a taxonomy of networks. And there were indications of it in the picture I showed where I said that the coefficients that we know about, the information that we have, is on the left and the right-hand side of the plot. And the structure that we don't know anything about is in the middle of it. And you want to see what possible different structures there could be in the middle. That's very vague, but it's a different kind of taxonomy, I think, than just these kind of order statistics of starting with degree and then going to clustering and then looking at other motifs and building up from that. So that's there's some articles you can read here. And now I'd like to ask your indulgence for just 1 minute, because I did finish a couple minutes early and we'll have time for questions. So if all the little people are gone, I want to make some totally bizarre speculations that might explain why I think this is such an interesting approach and why I really like working on it. So I've been good all through here. I haven't made too many outlandish claims, but here's the outlandish part. Especially when I'm working with power law parameterization, these are some things that I notice. First of all, the coupling constants, these really physical things like the strength of gravity or the charge on an electron, they can all be interpreted as rates in a Poisson process. One of these parameters in the inhomogeneous system acts like energy. It sets the scale of all the coupling constants. The other one is a resolution parameter, really, and it's related to the ratio of the strongest and weakest interactions in the system. So it's kind of like a Planck length or a time. And this unitarity principle, as viewing it as a symmetry principle and using it as a constraint on the solutions, gives you an entirely dual representation. Everything makes sense in either representation, but you can't get from one to the other for reasons I can't explain right now. So it's like what's on the other side of the light cone. It's out there. The world over there makes perfect sense. It's just not the one that we happen to be in. And also, when you make this transformation, the dual space, the strongest and the weakest interactions exchange roles. So I think there's something really interesting here that could lead to some very interesting physics. But I'll stop there. Everybody, pretend that you didn't hear that, and I'll go back to asking for questions.
Thank you, Stephen.
Thank you. So Stephen, the struts and cuts, you mentioned somewhere the reliability is submodular in terms of the cruxes themselves. So is there a representation where if you look at struts and cuts and then look at whether they share an edge or what fraction of edges do they share, you can map them to almost the nodes and edges space, but you're still maintaining. I mean, it's like going from graph to the phase space kind of a mapping, but here you're looking at the struts and cuts as the elements,
Yeah.
and then seeing commonalities. Is that representation useful to understand why some of these are happening?
Yes. Yeah, I think so. So for example, if you think of it in terms of the logical expression E, these things are the struts, the things in parentheses here. And the cuts aren't explicitly represented here, but if you looked at the negation of this, they would be the things in parentheses in the DNF form. And those are the structures, I think. So if you're looking at pathfinding, these are the paths, for example, through the graph that get you from S to T. And the way they overlap is the structure that you want. In this picture, the size of the first couple of cuts tells you these things. The size of the first couple of struts tells you those things. The way they overlap is what tells you these points here. And it's how many overlaps you're willing to try to compute that limits how far you can push these points. So there's some structural characterization in terms of just how do the paths overlap and how do collections of many paths overlap. Yeah,
in fact, I mean, to use a much more cruder analogy, like in the CI versus BI comparison that you were showing, it almost reminded me of an emotional serial killer versus a very pathological psychopath. Like one who is going after the most vulnerable or most easy targets, the most visible ones. The other is slowly cutting out elements that are common across struts or cuts, and then suddenly completely shattered the network.
Yeah, well, it's because they're all greedy algorithms, and these things are greedy in ways that aren't submodular, I'm pretty sure, whereas this one is. So it's walking around on this almost perfectly flat landscape, but it's headed for a deep hole. Whereas these,
it's greedy for a particular objective. Like the way you have defined the reliability is for a particular objective of V less than or equal to 200. So for anything else, it may not be good, but for this target, it's going for that hole.
Right. It's very expensive. I can't deny that. So if I went to V less than 199, I don't know. I've been working with Abhijit a little bit on whether the solutions nest or not. I think they would for some things, but if you took a completely different measure of effectiveness, then you'd have to start from the beginning again and rebuild this. On the other hand, that's a feature, not a bug, because it's not the case that the solution that you compute with CI or degree is going to be valid, correct for all these different things. So I'm kind of happy that it depends, importantly, on what you're trying to measure.
Okay, we are at time. Have a great day, everybody. Thanks again, Stephen.
Thanks, Stephen. Good talk.